Alright, so it's about time I made a second example video on how to solve first order linear differential equations. So, if you don't recall, they are of the form dy dx plus or minus p of x y is equal to q of x. So that's the form that we want for it to be a linear first order differential equation. And then, of course, you have the integrating factor, which is just called mu of x is equal to e to the integral p of x dx. And that's pretty much the gist of that. So, what do? We just multiply this whole equation by 1 over x, and the reason why is because we want it in this form, yeah, and there was no x multiplied by dy dx in the original expression, so we want to get rid of that, right? So, let's multiply the whole thing by 1 over x, so now it's just dy dx plus y is equal to x. Alright, it's now of the form some function of x multiplied by y, and that function of x is obviously 1. So, yep, let's do it. Now let's find out our integrating factor. So e to the integral of 1 dx is equal to e to the x. Alright, that's our integrating factor. Literally, that's our integrating factor. So the integral of 1 dx is just x, and therefore our integrating factor is e to the x. So it's now the now we multiply the integrating factor by the entire expression. So e to the x dy dx plus e to the x y is equal to e to the x, well, x e to the x actually. I'll put the x in the front because it looks nicer. It's just for, yeah, basically making it look nicer. But I don't need to do that thing where I just demonstrate that it is, this is the derivative of a product. All you need to know is that your integrating factor is, your derivative is, so like what you're doing is you're factorizing this into a derivative expression, like as if you're about to take the derivative of something that would give you this. And that's always just going to be the integrating factor multiplied by y. Remember how e to the x was our integrating factor? It's always the integrating factor multiplied by y. Always. You don't even need to think about it anymore. You just need to know that. And that's equal to, I just got a Facebook notification, man, I'm popular, man, god damn. X e to the x. And my handwriting is atrocious today, but nevertheless, integrate both sides. So that means e to the x y is equal to the integral of e to the x, well, x e to the x dx. So, this is why I chose this problem, because I have to do integration by parts. And I thought that was interesting, doing integration by parts in the middle of a linear first order differential equation problem. So, u is equal to x. And the reason why I'm choosing u to equal x is I know when I take the derivative of that, it's equal to 1, right? 1 dx, so the power disappears. dv is equal to e to the x, and whenever you integrate e to the x, it stays the same. So, I believe I have chosen the right one. So now e to the xy is equal to the integration by parts formula, x u v e to the x minus the integral of v du, and that's e to the x dx. And then that's the easiest integral in the entire world. That's e to the x y is equal to x e to the x minus e to the x, e to the e, sorry, that was funny, plus c. Yep. Cool. Now, all I need to do to finish off this problem is solve for y. But before I do that, I'm going to write e to the x y is equal to e to the x minus 1 plus c, because e to the x e to the x, and then minus e to the x, that's the factorization, so I just factorized it. And now y is equal to e to the x minus 1 plus c all over e to the x, and I can't cancel the e to the x because, you know, then I'd have c over e to the x. In another example, I'll probably solve for initial conditions, because that's probably a little more interesting than having a plus c. But yeah, that's the final answer. Y is equal to e to the x, x minus 1 plus c all over e to the x. And that's the end of the video, chaps. I'll probably include more. I'll start making more videos, obviously, as I'm on summer break. And I'm going to start making videos on Laplace transforms, hopefully. Exact equations, partial derivatives. I don't know. I think I'll be making videos and stuff. We'll see. But it is summer, so I have lots of time. And being a loser and loving math, this is kind of what I'm condemned to do. Anyway, see ya.